Welcome everyone. In this lecture, we will be seeing unsupervised learning. So, where machines find hidden patterns in data without any guidance or labels. So, unlike supervised learning that we discussed in the last lecture, here there are no teachers, only explorers. So, by the end of this, you will understand how algorithms can discover meaningful structures in data all on their own. Okay. So we'll be seeing unsupervised learning. Okay. So if supervised learning is like learning with a teacher who provides answer, unsupervised learning is like being dropped in a new city with no map. Okay, so you can relate to that example with this. So you have to explore and make sense of everything yourself. The machine looks at raw, unlabeled data and tries to find natural groupings or patterns. So this becomes incredibly valuable when we don't know what we are looking for in advance. So if you see unsupervised learning, suppose you are an alien researcher studying Earth's animals for the first time. With no prior knowledge, you might group them by number of legs, habitat, or size. So that's exactly what unsupervised learning does. It takes a raw data like customer purchase histories or genetic sequences and finds the natural categories. The most common technique for this is clustering, so which we'll be seeing next. What is this clustering? So think of this analogy. We have a group of fruits, so from which how it will be categorizing based on the features. So this is unsupervised learning. And so first we'll be seeing clustering, right? That is the most common technique used in unsupervised learning is. So first, why we need this clustering? Okay, we take off this real world scenario. A marketing team has customer data but doesn't know how to segment them. Okay, so clustering can automatically group similar customers together based on purchasing behavior. So this is invaluable because humans simply can't process thousands of data points to find these patterns manually. It helps us to discover the unknowns in our data, right? So how this clustering works? Think of clustering like organizing a messy room. So you might start by putting similar items together, that is books on one shelf, and then clothes in the closet, electronics in other area. Okay, so the algorithm does this mathematically by calculating how close data points are to each other in multidimensional space. So points that are closer together get grouped into the same cluster. Okay, and then we'll see here the k-means algorithm. So k-means algorithm is like a democratic leader. So it lets the data points vote on where the cluster center should be. So we start by randomly placing k leaders in our data space. Then each data point chooses its nearest leader, and the leaders adjust their positions based on their followers. So here this process will be repeating until the cluster stabilizes. Okay, it is simple, but it's a powerful one. So you could see how the k-means clustering example works. So first we'll see the steps of the k-means algorithm. So suppose we are clustering cities based on the temperature and humidity. First we randomly pick two centers, maybe one coastal and one inland. So then we assign each city to the nearest center. So you can see here. Next we recalculate the centers based on their members. So we repeat this until the centers stop moving significantly. So the result gives us meaningful climate clusters. Okay, and then from which we will be seeing determining the optimal clusters. So for example, here's take off this $1,000,000 question. How do we choose the K? Now choosing the K. So the elbow method. Okay. So the elbow method is like Goldilocks testing chairs. So we look for the points where adding more clusters stops giving us much better organization. So we plot the variance against the cluster count and look for the elbow bend. Too few clusters oversimplify, too many overcomplicate. So we want just the right one, right? So that you are going for this hierarchical clustering. So it's like building a family tree for your data. It starts with each point as its own cluster, then progressively merges the closest pairs. So we visualize this in dendrograms. Those tree-like diagrams, we will see that. So this is a dendrogram. The height where we cut the tree determines how many clusters we get. So it's particularly useful when we don't know how many clusters to expect. Okay. So these are types of hierarchy clustering where we have divisive and agglomerative. So it's a top-down clustering and bottom-up clustering method. And then we'll see DB scan algorithm. So it's a rebel of clustering algorithms. While k-means forces everything into clusters, DB scan acknowledges that some points might be noise. It finds dense regions separated by sparse areas. So much like identifying cities on a population map. The key parameters are epsilon here. So that is how close points need to be and minimum points. How many points makes the cluster. Okay. So if you see this is about the DB scan algorithm, and it's this is one of the example of this. So we see, however, unsupervised learning is not a magic one. So results can be hard to interpret. The clusters exist mathematically, but their meaning is not always clear. It is also sensitive to parameter choices and distance metrics. So unlike supervised learning, we often don't have clear ways to evaluate the performance since there is no ground truth for this. Okay. So this unsupervised learning is an uncharted territories in our data. Whether we are using k-means, hierarchical clustering or DB scan, the goal will be the same: to discover the hidden stories our data wants to tell. Okay. So that is all. Thank you.